Hello, good morning, good afternoon, and good evening to everyone who's tuning in. Hope you're doing well and staying safe. On behalf of Biopatro Arab Oil and Gas Academy and SPE Egypt section, I'd like to welcome you all in our second session of our summer internship. I am Mayor Tariq, gas and petrochemical engineer student, and I'll be your moderator for today. Before we start, I'd like to remind you to drop your questions in the Q&A section below and to keep the chat box professional and ethical. So without further ado, let us welcome Dr. Yasser Shaib, who will be giving us a session on the stability of underground caves and tombs. Dr. Dr. Yasser Shaib is a professor of engineering at the American University in Cairo and the former chief of party of the Center of Excellence for Water. Professor Shaib has always been active in the field of culture, heritage management, and conservation, risk assessment, and project management through the participation and management of several international projects in those fields. He was also the director of the Egyptian Center for Documentation of Culture and Natural Heritage between 2012 and 2014. Between 2006 and 2019, Dr. Shaib was the Egyptian National Coordinator of EU programs on higher education. And since 2006, he was highly involved in the setting up of the Euro-Mediterranean policies and dialogues on higher education, research, innovation, and culture. As a focal point of many Euro-Mediterranean programs in Egypt. Dr. Yasser is the graduate of Cairo University in 1990 with a degree in engineering and had a PhD from Nancy School of Mines in France on the contribution of fuzzy logic to geotechnical risk assessment of some ancient tombs at the Valley of the Kings in Egypt. Since his early years, Dr. Shaib have developed a passion for various fields of science and knowledge this dissemination. Thank you so much, Dr. Yasser, for coming today, and the mic is yours.
Okay, so thank you very much, Engineer Mayar. Thank you very much, Dr. Ahmed, for inviting me for this second session. Today, I'm going to be speaking a little bit in details and in technicalities of rock mechanics and geomechanics about how to make some calculations, some basic calculations for underground tombs and caves. And yeah, I mean, this will be the agenda for today. That today I will be speaking about the stability of tombs and caves, and I'll give one or two cases, I think, at the end about things that happened. At the beginning, I'll be speaking about differences between caves and tombs. I mean, when I speak about tombs, of course, I speak about ancient Egyptian tombs. I'm not the regular tombs that we use. I mean, that people use every day. But I'll be speaking about ancient Egyptian works and tombs that happens in Egypt, and what's the difference between a cave and a tomb. Then I will be giving you some accounts about the stability of underground structures, and in terms of analytical methods. And then later on, I'll be speaking about some empirical methods and numerical methods for the stability of underground structure. And finally, a case or two from Egypt about those calculations. Now, to start the presentation, the main difference actually between a cave and a tomb, an underground tomb, let's put it this way, is that the cave is a natural structure. It's done by nature. It's not done by men, although some caves are dug actually by people, by humans. But the majority of the caves that we see today in many countries around the world are actually done naturally. And the way it happens is that usually you have a kind of limestone or a sandstone, and this limestone with time, with some chemical processes, the limestone becomes more and more friable, and it dissolves in water, and it moves with the water. So you have like a void that is in the underground, and then with time the water comes in. With time, I mean, things happens and vegetation comes in and so on and so forth, and you have actually a cave. This cave could be as small as, 1 cubic meter, and it could be as big as thousands of cubic meters. Actually, you can see big caves. I mean, I've been to big caves in Lebanon. I've been to big caves in the US. I've been to big caves in France. And I've been also to small and big caves in Egypt. And as I said, I mean, the size of the cave is really, it's variable. I mean, there's nothing special about it. But the main characteristic is that it's done naturally. I mean, there is a natural processes, natural geological processes that leads to the making of caves or the existence of caves. And I'm here putting some photos about those caves, and maybe if you have studied geology, and I bet that all of you probably have studied geology before, then maybe you have heard about the term stalactites and stalagmites, which are calcium carbonates, or let's say carbonates, that are formed in those caves also naturally with the effect of water. And I will show you some pictures, some real pictures of those stalactites and stalagmites from Egypt. So this is a photo that is taken in one of the caves that we have in Egypt, in the governorate of Beni Suef, which is, something like 150 kilometers south of Cairo. And this cave is called Sanur Cave. It's naturally formed. It's underground, as you can see it here, and it's big. This is why I'm putting my photo actually here to give you an idea about the size of that cave. Here again, here I am. I'm standing inside that cave in order to show you as well the scale, and you can see those are the stalactites that are coming from the roof, and those are the stalagmites that are coming from the ground. Actually, they are not coming from the ground. They are coming because water is dripping from the from the roof on the ground. And while this water is dripping, it carries with it very small fragment, nano, maybe scale size of carbonates. And those carbonates are deposited one after the other, after the other, after the other, after the other. And at the end, you have this formation that we call stalactite. Sometimes the water is actually dripping on the ground. And when it drips on the ground, the water evaporates, or the water dissipates, and it leaves small portions of that carbonate material that it carries, and then it comes up until it gives that. I think I have another photo. Yes, this is another photo of the same cave, and you see clearly here the stalactites, and maybe if you observe very well here below, it's the stalagmite. This is a natural reserve that we have in Egypt. In other countries, like in Lebanon, for example, there is this cave called Jaita, where you can actually go inside and look into it. There is kind of lightnings and a tour. You can take a tour in it, and it's really very nice to be there. Again, I insist on the fact that it is always naturally done. I mean, it's not man-made at all. Those are some photos again from the Sanur cave in Egypt, and also we have this phenomena that happens here that is called a sinkhole, which is you have a cavity in the ground, and then all of a sudden the bulk of the ground is actually falling below. And this is also, it could be very, very dangerous. I mean, here, luckily, we are inside a cave that is in a remote area, that no one is living there, nothing's there. But sometimes those sinkholes actually happens as well because of the existence of cavities, and they are, they destroy homes and property. If you would search Google on the word sinkhole, you will find a lot of photos, a lot of very frightening photos, big sinkholes or small sinkholes, and it is actually problematic, and it is a result of the existence of a cavity below the ground. So the ground just fall into this hole, if we can call it a hole. Now, I will not go into details now about this. Now, underground tombs are not naturally done. They are man-made. And since they are man-made, they have a form, they have a structure, they have a place, they have dimensions and so on and so forth. And if you have attended the first lecture that I given, This is the same picture that we have for the one of the ancient Egyptian tombs in Saqqara in Egypt, 25, 30 kilometers south of Cairo, and this is how it looks in real life, and this is how it looks to me as an engineer. So I just take the abstract of it. Those are like geological layers, and then some tunnels that are running through those geological layers, and maybe some objects that are put in here, and then some cracks in those geological layers, and so on and so forth. And this is sandstone, this is shale, this is clay, this is limestone, this is overburden. So this is how I see it as an engineer. So the main difference again between a tomb and cultural heritage tomb, let's put it this way, and a cavity is that the tomb is man-made. It has a definite structure. We know about its structure, while a cave, it's naturally made. So usually its structure is more or less following a random form, I would say. Now, how to assess? This is another photo of another tomb in Egypt, and this is a third photo. As you can see here, it's going a little bit deep, and you can, if you look here, this means that this place over there is like deeper than this place in here. Maybe it's like 30 meters or 40 meters below the surface. Nevertheless, it's still very stable, and people can go in, and people can visit, and people can admire the colors and the paintings on the walls, and so on and so on and so forth. Now, this is what exists, and this is the domain, let's put it this way, that I will be trying to speak about today. Now, how to assess the stability of those structures. Okay, I've been into the Sanur cave, I've been into the Jaita cave, I've been into the tomb of Ramses I, Ramses II, whatever. But the question that I usually ask as an engineer is how to assess, how to make sure that this structure is stable, that it will not fall on me, it will not fall and will destroy me, or will kill me, or will destroy anything that I will put there. It will not fall and will destroy everything that is in there, and destroy the property and the paintings and everything. So this is the main question that we are asking. Again, if you remember the lecture of last time, we spoke about the problems that are facing structures, and I'm putting here some of the elements that affect the stability of an underground structure. So we have groundwater that is definitely affecting a lot the stability of the rocks around this opening. You have the joint persistence. You have the strength of the rocks that are around this opening. You have the joint orientation, because if you have joints that are, if you have layers and joints that are inclined to the opening, is more dangerous than layers that are more or less horizontal. You have horizontal stresses that are resulting from some tectonic activities. You have generally the discontinuities and the discontinuities of the rocks that are in here. And then you have also the time. And I think last time I spoke, that in the last lecture, I spoke a little bit about the time as well. Now, another thing to be considered when you are speaking about an underground structure is how wide it is, what is its height, and how far is it from the surface. So here we speak about the thickness of the overburden. We call it the thickness of the overburden, which are the layers that are above this opening. And here, sometimes we speak about underground structures that are 5 meters from the surface. Sometimes we speak about underground structures that are like 100 meters or 200 meters from the surface, and still we are able to build it, and still we are able to go into that one. Now, when we speak about this, we need to consider as well the width of the cavity, or the width of the tunnel, or the width of the tomb, and we need to also to think about the height of that cavity and or that tomb or that tunnel, because all those parameters, in addition to those that were in the slide before, are actually affecting those ones are actually affecting the stability of that underground structure. And usually when you dig a tunnel or a tomb inside a medium of rock, you have stresses. You create additional stresses that are subject to this opening. And usually the question is, will this structure normally, without any additional support, will it support or will it bear the stresses or the forces that are acting on it or not? This is actually the problem of stability. So we're speaking about forces that are acting on an opening, and we're speaking about resistance that we put there, or the natural resistance or artificial resistance. And we need actually to make some calculations. So we need to calculate the forces, and we need to calculate the resistance that you are putting in that place. And when the force is acting on the opening is larger than the resistance, this means failure. If the force is equal to the resistance, this means equilibrium. This means like almost there. And if the force are less than the resistance, then this means stability. So those are the three cases that we usually have. And since we cannot really control the forces that are acting on any underground structure that we have, because it's nature, it's layers, it's the water that exists, it's the discontinuities that's naturally there. It is. What we can actually control, what we can actually try to calculate and try to enhance is the resistance. So if you will find that the forces acting are larger than the resistance, then you need to increase your resistance in order to make your structure stable. And if not, you know that it will fall. If you find that the resistance that you have are larger than the force that naturally larger than the force that are acting, means that the force are less than the resistance, then you have nothing to lose. You have nothing to worry about. It will be stable. There will be no problem. And this is actually what we use in the stability of those. Now, the question or the problem is how to calculate those forces, because resistance I can calculate, I can moderate, I can try to install probes, I can try to install some metallic structure, some wooden structure, whatever structure I can put. But what I cannot control is actually the force. What I cannot know is the force. And this is the main issue of those who are working in rock mechanics like myself. How to calculate the forces that are acting on an underground structure. Now, there is, of course, I mean, I am not the first person, and I will not be the last person that have thought about this idea, about this problem. There has been people thinking about those problems since many years. The very well-known professor called Terzaghi in 1943, like 80 years ago, he developed this this theory, saying that in order to calculate the force that are acting on an opening like this, you don't actually calculate everything. You need to consider the distance to which is the height, the distance to the overburden, the height of the opening, and you need to consider 45 degrees minus phi over 2. And phi over 2, I mean, phi, I don't know if definitely you have studied maybe rock mechanics before, or you have seen the Mohr circle of, or the Mohr envelope for rocks, for stability of rocks. And the phi is actually the tangent to the Mohr envelope. So it's the angle between the horizontal axis and this line that is tangent to the Mohr envelope. And you divide phi by 2, and it's 45 minus phi by 2. So this is, you calculate the weight of all this mass of rock, and this is the force that is acting on this opening. Now, if you will calculate this, and you will know how much the rock, or how much the rock can resist, can support, can take on itself naturally, then with the difference between those two, you can work on the equation that I spoke about before, which is Yes. So now you have the force and you know the resistance, so you can deduct if it will be stable or if it will not be stable. This is an analytical method that has been, as I said before, invented by Professor Terzaghi in 1943. Of course, it has a lot of details that you can look at in the literature. You can study it in the literature and see how it is applicable. Now, this is again the continuation of the theory of Terzaghi, because he says that if the distance from the surface to the opening is higher than a certain threshold, then you don't actually calculate the weight of everything, because here we have calculated, as I said before, you need to calculate the weight of everything that is above this opening, with this inclination and everything. But this is when the distance between the opening and the surface is empirically about 5 times your opening. So if the opening that I'm putting here is like 2 meters in height, and this opening is situated at 10 meters below the surface, then I need to calculate everything. If this opening is 2 meters in height, but it is situated at a depth of like 50 meters below the ground, I will not calculate everything. I will here rely on this cone or this arch of what is called here the arching zone of Terzaghi. Actually, it's called, we call it like this, the arching zone of Terzaghi. So this is the only part of the rock weight that has to be supported by this opening. So you don't support everything. You don't calculate the weight of the rock until the surface. You just calculate this cone of rock, and this will be the force that are acting on your opening. And again, now you know the force and you know the resistance, and now you can deduct if this will be stable or if this will not be stable. And of course, Terzaghi 1943 is very famous, and it's a very famous theory, but it's not the only one. And there has been a lot of iterations and a lot of enhancements to that methodology. So if you look into the literature today about like books that are published this year or last year, you will find this theory, but you will find also a lot of extensions to it. They would say, no, actually, it's not B1 like this. It's like B1 minus something, small something. So we have made some studies. We have enhanced this cone. It's actually not phi over 2. It's actually phi over 2.01 or something, because we have, with time, with development of science, we are able to enhance those equations, and we are able to come with maybe better estimates of the forces and the resistance. But I mean, if you will calculate it with the cones of Terzaghi, you have a very good and fair information that you can really work with. Now, again, this is again the same theory, I mean, but with some enhancements. So this is Beer-Bohmer in 1973, after another professor called Zicki, and in here you have maybe another formula which tells you what is the alpha here that you need to take into consideration. And you can see that there is a difference actually between this cone here, I mean the shape of this cone here, and the shape of this cone here. And this is, to be blunt, this is the result of 30 years of research that are separating Terzaghi from, I mean, this one is 1973, and this one in 1946 or 1943, the one that was before. So in 30 years, we came up with an enhanced equation, an enhanced shape based on other research and other things. And this is usually what happens in all fields of research. I mean, you have something that is very old, that is done 19 something, and then with time, you make other research, you enhance the equations, you have better equations, and so on and so forth. So this is again the example of Ziki in 1973, cited by Pierre Bomer. I think this paper is like 1980, 80 something. And I'm sure again that if you look into a book that is published about rock mechanics and how to calculate the forces around an underground opening that is published maybe in the year 2020 or 2022, you will find a slightly different equation than this one that is taking into account something more, and you can of course use it. Now let you take you to a look into some empirical methods and empirical models, or what I would call an empirical models, because empirical models are easier to apply. You don't have a lot of mathematics to apply, and they are mainly based on experience. So you have very experienced person who have worked with like 30, 40, 50 sometimes years, that have worked with underground structures, underground tunnels, underground tombs, underground temples, whatever. And with their experience, they are able to derive some rules. That's why I call it empirical models, because you don't have a lot of equations into it with respect to what I've just shown you about Terzaghi and Ziki. Now, the very famous empirical model for underground structure to calculate, to know if an underground structure will be stable or not, is a system that is developed in 1978, I think. No, 1989, yes. I think it was before, but maybe this table was 1989. But yeah, let's put it this way: it's in the late 1980s. It's developed by Professor Bieniewski from South Africa, and after like 40 or 50 years of his experience in working with underground structures, he derived this system that is called rock mass rating. And the rock mass rating is a system, according to him, that would give a rating for any type of rock. So if you have a rock that you would like to build to dig your tunnel in, if you know its mass rating, rock mass rating, then I will show you in the slide afterwards. Then you can know how much time this rock will support, how much time this environment will require. How much time this opening will be stable until it requires some reinforcement, for example. And it goes very simple. I mean, you look into the strength of the rock material. So if you have a uniaxial compressive strength, and you can calculate this, of course, in laboratories and so on, or if you use the point load, which is also another type of testing for the rock. So you bring a rock mass and you test it in a laboratory, and it will give you the resistance of that rock. So if the resistance of this intact rock is more than 250 megapascal, then you give it a rating of 15. If it's between 100 and 250 megapascal, you give it a rating of 12. If it's between 50 and 100 megapascal, you give it a rate of 7, and so on and so forth. So let's make a hypothesis that we have a rock that has a uniaxial compressive strength that is like, let's say, 200 megapascal. So 200 megapascal is rating of 12. So let's put the 12 on a piece of paper with us, and let's proceed. Now comes another parameter that as well Bieniewski spoke about, which is the rock quality designation. And this rock quality designation, it designates the amount of fractures that you have in 1 meter of rock. And I would like, if you want to go deep into this topic, you can search on the internet on RQD, how to calculate RQD for rocks, and you will find a lot of photos and a lot of materials for that. But let's assume that for us, our rock that we have has an RQD of 95%. So if it has a 95%, then I'll give it a rating of 20. So I had 12 before, now I have 20. Let's add those two together. So we have like 32. Let's put them on a piece of paper and let's continue. Now, it speaks about the spacing between here. I mean, in parameter number 3, we are considering the spacing between joints. If the spacing, the average of spacing between two joints that I can see in the rock are more than 2 meters, then I'll give it a rating of 20. If it's between 0.6 meter to 2 meters, then I give it a rating of 15. If it's between 20 centimeters and 60 centimeters, I give it a rating of 10, and so on and so forth. So let's assume that our rock has a joint spacing, or not our rock, our environment have a joint spacing of about, let's say 50 centimeters in average. So I'll give it a rating of 10. Okay, and I'll keep this 10 on a piece of paper. Now, the next question is conditions of discontinuities. What are the conditions of discontinuities? And you have here examples: very rough surfaces, not continuous, no separation, unweathered, and so on and so forth. And you have the rating here. Then you go for the last one, which is groundwater. And in groundwater, you know how much groundwater that you have in your rock, and also you have the rating that is in here. Now, suppose that we had here a rating of 12, a rating of 20, that's 32, and then a rating of 15, that's 32, and 15, that's 47, and then we have here like 20, so 67, and then I have here a rating of 10, and so I arrive at the end at 77. So I calculated my rating for my environment as 77 rock mass rating. So this 77 is a very important number that I will use in the slides that comes in order to know about the quality of that rock. Now, here it says again, Bianiewski in 1989, it says that if your rock mass rating is between 81 and 100, we call this a very good rock. If it's between 61 and 80, like our case was 77, this we will call it a good rock. So what's a good rock? A good rock means that if you have an opening, as it's written here, of 10 meters, so 10 meters width, you can advance this tunnel about 1 to 1.5 meters, and it will not fall. It will just stay as is. And if you want to make rock bolting, then you can make like support for the roof every 2.5 meters. And we have here also this graph that says how much time will my opening stand. So if I have my opening that is 77, as we spoke before, so this is 60, this is 70, this is 80, so 77 would be like here. So you have like a line, a dotted line, you can draw a dotted line like here, and it will tell you that with an unsupported span of about 20 meters, it can stand for 10 to the power of 4 hours. 10 to the power of 4 hours, I think this would be like months or something. So this means that you can have an opening that is about 20 meters in width, and it will stand alone without anything for like months without any support. Of course, if you wanted to stand more, then you need to support it more. Again, this system is empirical. It's based on experience of Bianiewski, but it is widely used around the world. When I go around in places and people ask me, or I ask people, what is the quality of this rock? And they will tell me this rock is a fair rock. I know exactly what they are speaking about because I have this table. I mean, we in rock mechanics, we have this table here that tells me a fair rock is within those two limits, 41 to 60 rock mass rating, and you can. So you have like a code that we can that you can work with. So it's not left to a personal experience. It's actually based on experience of many years behind. And again, this was Bianiewski in 1989 or 1985. From 1985, 1989 until now, a lot of enhancement has been done to this methodology, but it stays, it stays as one of the very established tools to assess how much time the rock mass will stay and how much time, how big the span that I can do in this place. This is a different system that is actually established by another professor called Barton. And he has also established another system that is called the Q system. So, but it's the same. So you make some calculations, you make some ratings, and then when you have this rating of Q, you can actually know if your rock will stand for how long, and if your rock will stand for this and that. Again, all of this is based on experiences, is based on years and years long of experiences. No equations behind like Terzaghi or Zicchi before, but here you have a lot of experiences put on. Now, with the advancement of computers in the 1980s, personal computers, 1980s, or even computers, 1970s, and the personal computer, 1980s, 1990s, and 2000, and today, computers, we started relying on numerical methods. We thought, why don't we calculate everything numerically? Why don't we calculate the stresses and the forces in a numerical way? And this is actually what we do today. I mean, most of the people today would work with numerical methods. And here I will be showing you two main numerical methods. Maybe you've heard about one of them, which is the finite element method. I mean, it's very widely used in mechanics or mechanics of material, because it assumes that the whole rock mass is a continuous medium. That's why it's used in mechanics, because it's assumed that everything is continuous medium. So you have an opening like this, and this opening is subjected to forces that are coming from, this is the boundary conditions. So you divide this medium into small pieces, into small elements like this one. That's why I call it the finite element, because it goes into very small elements. And numerically, for every element of this medium, we start calculating the forces and the stresses. So we take every one of those small pieces here and there and here and there and here and there, and we start calculating the forces and the stresses. And once you calculate it for this element, you go to this element, and you go to this element, and you go to this element. So you are calculating actually the forces acting on this element from everything that is around it. And then when you go and calculate for this one, you will take into consideration everything that is around it, but also you'll take into consideration this one, and then this one, and then this one, and then this one, and then this one. And then you move, you finish the first, let's say, round, then you go to the second round, the third round, the fourth round, and so on, until you reach the outer boundary conditions. And from this, you can actually have an idea about the state of stress that is in here, the forces that are acting on this opening. And as I said at the beginning, if you know the forces, you know the resistance of your rock, then you can calculate, or you can know if the force are more than the resistance, then it will fail. If the force are equal to the resistance, then it's equilibrium. If the forces are less than the resistance, then it's stable. And this is actually what's done. Now, in rock mechanics, we know that we have a lot of discontinuities. We have a lot of fractures. We have a lot of layers. We have geologically, we have a lot of layers. We have a lot of discontinuities, and so on and so forth. That's why, I mean, some people, a lot of people use the finite element method, but I think it was the late 1990s, where a group of researchers in Minneapolis in the US have invented another methodology called the distinct element method. And there is actually softwares that can do those calculations. And the distinct element code or method, it acknowledges the fact that natural medium like rocks are full of cracks, full of layers, full of discontinuities. So what they do is that they would treat every block or every element. That's why they call it distinct element. They will call it, you will call this element as a distinct element. It has a size, length, width, and depth, and it has also forces, and it has resistance, and so on. And then we will start studying the interactions between those elements together. So I have element A and element B, and I'm starting to study the interaction of element A and B together, and then element A and B, and then element C, and so on. So I'll take this element here, and I'll study the interaction between this element and all of those that are around it, and this element and all of those that are around it, and so on and so forth, like it's said here. And those interactions are usually either tension, are either compression interactions, like they are pushing against each other, or they are separating from each other, so like tension, or they are moving in a shear with each other, or they are actually, I mean, the forces that are actually a combination of the three that I'm speaking about. So there is tension, there is compression, and at the same time there is shear, and there is torsion, and there is so on, so on, so on, so on. So I'll take every element, I'll try to study its interaction with all the elements that are around it and how it is affected, and then I will be able to calculate all the forces that are acting on my opening that is that is in here. Now, the results are results like this. This is a result of, I think this is a finite element code, because it seems to be a continuous medium. While here we are speaking about maybe no, I think both of them are speaking about finite element code, because here you see it's completely I mean, there is no discontinuities, and here also we don't have a lot of discontinuities apart from that one and that one, like two layers that are separating it. But we know, I mean, geologically we know that this rock here is not actually a continuous medium. It's a lot of fractures and a lot of joints. But I mean, this is the result that we get. So we get the direction of the stress, we get the amount of the stress, we can see it here, and then with the amount and with the direction of the stress, we can design the support that is needed, or we can actually calculate if it will fail or if it will not fail. If we speak about this thing, this is again finite element code. And yes, this, I mean, sometimes we do it in 2D, sometimes we do it in 3D. I mean, different softwares. And here there's a software called Plaxis. There's other, I mean, there's like, I would say 10, 20 softwares that can do this thing. And you can also fabricate your own tools. And this is what we do actually when we design a support system. I mean, in this opening, we have designed a support system that is the roof bolting. And with the roof bolting, we recalculate everything again to make sure that it is stable, that the displacement will not go beyond something that you know. Now, maybe I will go quickly to the cases, because the last time I was here on Monday, I spoke about this case of the Serapeum, and I show some graphs, and we can see them here. Again, it's the Serapeum tomb in Saqqara in Egypt. And we go quickly. Yes, those are calculations that are done with a universal distinct element code software. And you can see here that we have blocks, different blocks, here different blocks, here different blocks, here different blocks, here different blocks. And with the calculations, you can have actually two main results. The first, or actually more than two main results. You can have the direction of the stresses, because if you want to design a support system for this tomb, you need to know where the forces are coming from. And if you will know where the forces are coming from, then you can put your support system against that force, directly against that force. So that's why it's important to know the direction of the force or the stress. Now, this is one thing. The other thing is the amount of the force that is acting. And the amount of force, of course, that is acting. And you calculate, as I said at the beginning, you calculate the resistance of the rock or the additional resistance that you'll put and you ensure the stability. The third thing that we get actually from such a study is that we can know which blocks will detach first. So if you have an opening like this, with this study, we will know that the first block that will detach is actually this one, and then this one, and then this one, and then it will go in like this. So if you want to design a support system, then I would advise in this case that you will be interested in this block that is in here. You just support it with a roof bolt maybe, or with an anchor, and it will stop, and it will be stable, and everything else will be stable. So this is again an advantage of this of this thing. Now, I know that today I went very fast into maybe the calculations and so on, because I didn't want to overburden you with a lot of calculations like additions and multiplication and so on and so forth. But I have gathered here all the resources, all the papers, all the literatures, all the books, all the journal papers, or the websites that speaks about this this topic of stability of underground structures. And you will find here maybe sometimes books. This one is Practical Rock Engineering, Rock Mass Classification. This is a chapter in a book. You can find here, this is maybe a paper that is in ResearchGate. And I mean, everything that I have spoken about, everything that I have shown you the last time and this time is actually has its reference here in this in this slide. With this, I actually would like to thank you. I have finished, and today I have covered those topics. I mean, briefly speaking about caves and tombs, what are the difference between the two? How we assess the stability of underground structures. Then I went into generally what are the factors affecting those. And then I went into the analytical models, mainly the Terzaghi and Siki. And then the empirical models, mainly the Bianivisky and the Q system. Just rapidly, I went through it. And then numerical models, I spoke about a little bit about finite element methods and distinct element methods. And I show you the case of the Serapium from Egypt and how did we calculate that for it. I'm very much open for any questions if you have any questions.
Thank you, Dr. Yasser, for this informative session. Thank you so much. And we have 3 questions.
Yes, please.
Can we apply some formulas for tunnel building?
Of course. I mean, of course, all of those formulas are applicable in any underground structures. I took the cases that I'm speaking about because I'm very much interested in cultural heritage and stability of cultural heritage and so on. But I mean, everything that I spoke about today are applicable to tunnels and to any other underground structure. Yes.
And how we can follow the evolution of the forces and resistance of the rocks as a function of time of underground structures?
The function of time is very interesting thing, because we know that with time things deteriorate, and there is a lot of research that is done on the effect of time on the stability of underground structures once we have done it. The basic element is that we monitor. Once we have an underground structure, a tunnel or a tomb or whatever, we monitor. I mean, we designed this, we made our calculations and so on and so forth, and then we calculate the resistance and we put the support in place. Once we put the support in place, I mean, usually we don't put a support that is equal exactly to the forces. We increase it in order to have a factor of safety of more than 1, and then we start monitoring the evolution with time. There are a lot of literatures that are speaking about the evolution of time. I mean, in 10 years, it will deteriorate. I mean, the resistance of the rock will deteriorate of about 5% or 10% or 16% or whatever. But this is, I mean, you can find this in the literature. But the basic idea is that you monitor once you design an underground structure, you monitor its evolution. And with this evolution against time, you can actually predict that, yeah, in 50 years, I will have a problem in this place. So I need to maybe to work about it in 10 years from now. But it's a very interesting topic, the time, yes.
Okay, and the last question, how is the groundwater affects the stability of the rocks?
Well, the groundwater actually affects the stability of rocks in two ways. When you have joints, and those joints are, joints between two rocks. I mean, you usually, what stops the joints from moving, from the rocks from moving from each other, is actually the friction. And the problem with the water is that with water, this friction is decreased. So it acts as a greasing material. So, I mean, you can test it at home. If you put your two hands against each other and you try to friction them like this, it will be a bit difficult, I would say, a lot of heat. But if you have the same hands underwater and you apply the same force, you will find that the water is greasing actually the rock material. So this is the bad effect. I mean, this is one of the bad effects of the water. The other bad effect of the water is that if the rock is very porous and it has a lot of water in it, it will increase its weight. So my hands, the weight of my hands are, let's say, 2 kilograms. If I will put my hands in water and everything is porous, and I have a porous hand, which is not the true, but the weight of my hands will be heavier. If you get 2 pieces of limestones and you submerge them into water, you put a lot of water inside their pores, they will be heavier than a dry limestone. So the water usually have 2 effects. One first effect is greasing of the joints, and increasing the weight of the rocks itself.
Thank you so much, Dr. Yasser, for your great effort. And noting that this session will be uploaded soon on Biopatro YouTube channels, so make sure to subscribe on our YouTube channel. Thank you all for your attendance, and bye.
Thank you so much. Thank you, Mayar. Thank you, Dr. Ahmed.
You're welcome. Bye.